Hello and welcome back to our class on algorithmic game theory. In the last lecture we introduced congestion games, and we also showed that every congestion game always has a pure Nash equilibrium. Today we will start discussing the question whether it is easy or hard to compute such an equilibrium. This is actually an important question because, well, if an equilibrium is easy to compute, then, well, it is likely that players actually do play this equilibrium. Whereas, well, if it is hard to compute an equilibrium, then, well, this is a rather strong assumption. And as a matter of fact, in general, as we will show later in this class, it is hard to compute an equilibrium, but for some special cases, there are polynomial time algorithms. And this is what we will show today for two very interesting but easy special cases. But before we start with this, let's first recap what we learned about congestion games last time. So first of all, what is a congestion game? A congestion game consists of these four elements, namely a set of players, n, which we usually call 1 through n, a set of resources. We always say these are m resources. These might be edges in a graph, for example, but this might also be something else. And then every player has a strategy set. What is that? The strategies are subsets of the resources, meaning that the strategy space is a subset of the power set of the resources. And every resource has a delay function which maps the number of players using this particular resource to an integer. And this lets us define the cost of player I in a state. What is a state? A state is just a choice of a strategy for every player. So this is a vector of n strategies coming from the Cartesian product of all strategy spaces. And what is now the cost of a player in such a state? Well, it is defined as follows. Take the sum over all resources that this player is using in this particular strategy in this state, and now add up the delay functions evaluated on the number of players that use this particular resource. So this is what we write by nr of s. That is the number of players that use resource r. And we now take dr of nr of s. This is the delay of resource r when nr of s players use this resource. And then we defined a pure Nash equilibrium. A state, meaning such a vector of strategies, is a pure Nash equilibrium if no player can unilaterally improve his or her cost. What does this mean? Well, the cost that player I incurs in state S is at most what he or she incurs when switching unilaterally to a strategy Si prime, while the other players still use strategy S minus I. And this holds for all players and all deviations, all alternative strategies that this player might be deviating to. And we showed that there is always such a state, which is a pure Nash equilibrium. How did we do that? Well, we used this Rosenthal potential. This Rosenthal potential is defined as follows. We take the sum over all resources, then we take this sum from 1 up to the number of players using this resource in the current state, and then we add up the value of the delay function for this particular number. And why was this important? Well, this was because of this following lemma. We showed that whenever only one player changes his or her strategy, then the change in the potential is exactly the change in the cost of this one player. And this helped us show that any improvement sequence has to be finite, because whenever one player improves his or her strategy, well, his or her cost goes down, but this also means that the Rosenthal potential goes down by exactly the same amount. And this means that whenever we follow such an improvement sequence, the Rosenthal potential goes down, and eventually we have to reach a state at which it cannot go down any further. So let's now talk about potential algorithms to compute such a pure Nash equilibrium. Actually, one of these algorithms is already implicit in our existence proof. Namely, we show that any improvement sequence is finite. So this means that, well, we could just find an equilibrium as follows. Start from any possible state, and then just follow an improvement sequence up to the point where you cannot improve any further, and we know that this is a pure Nash equilibrium. Is this a polynomial time algorithm or isn't it? Well, as we will see, it depends on what game we are talking about here. This depends on the structure of the game. So what is now important? Well, the important question is, of course, how long will these sequences be? And we've already seen an upper bound on the length of the sequences, namely exactly in our proof. So let's write this down. The bound that we showed last time was 2 times the number, the sum over all resources, the sum over all numbers from 1 to n, and then the absolute value of the delay resource r evaluated at k. Or alternatively, we could say, okay, this is 2 times the number of resources times the number of players times the maximum value of all r and k of the absolute value of dr of k. So this means we are talking about the highest absolute value that any delay function ever takes. Is this a polynomial bound? No, it isn't. It is only pseudo-polynomial in the language of computer science. Why that? Because this depends on the size of the numbers. So it is easy to represent a number such as 2 to the 10 by only 10 bits. So a guarantee that depends on 2 to the 10 wouldn't be polynomial, but it would only be 10 that would count here. Because we are talking only about the number of bits we need to represent this. So this is not what we're looking for here, although this will be helpful in a bit. There is another upper bound that we can use, namely, what do we know? Well, we know that any improvement sequence is finite, and what's an upper bound on the length of an improvement sequence? Well, it cannot see any state twice. So the number of states is also an upper bound. And how could we write this? The number of states, that's just the cardinality of the Cartesian product of all strategy spaces. So this is upper bounded by 2 to the m times n. So clearly this is finite, but it is not a polynomial bound in m and n. So are there actually improvement sequences this long, or is this just a bad upper bound? No, there are actually improvement sequences this long. Let's see this in an example. We take only one player. So this means that n is equal to 1. And we now consider the following graph. We have a source, and then we have a sequence of parallel edges, namely these are k plus 1 pairs of parallel edges. So how many resources are there here? For every edge corresponds to a resource, so we'll have m equals 2 to the k plus 1 resources here. But there are 2 to the k plus 1 many strategies. Why that? Because this one player somehow wants to get from the source to the sink. And how can he or she choose to get there? Well, for every of these parallel edges, the player might choose to either use the top or the bottom edge. And this gives us 2 to the k plus 1 strategies in total. And now there is a, well, admittedly contrived example of a long improvement sequence. Namely, what can happen? Well, initially the player might use all the top edges. What's the cost at this point? Well, it is 1 plus 2 plus 4 plus up to 2 to the k, so it's 2 to the k plus 1 minus 1. But then it is actually an improvement to only switch to the bottom edge for the very first pair of parallel edges. This increases the cost. Admittedly, it decreases the cost only by 1. And then, from that state onward, it is an improvement step to switch again to the top edge, but switch to the bottom edge for the second pair of parallel edges. Also, this decreases the cost by 1 because, well, on the first pair we now have an increase by 1, but on the second pair we have a decrease by 2, so in sum the cost decreases by 1. So this is clearly not a best response in the sense that this is the best thing that we can do, because eventually we could we could actually immediately switch to the all bottom path, but the only point I want to make right now is that there can be long improvement sequences, and this is an improvement sequence because we are improving in every single step. So how could we write this? We could write this as kind of a bit counter. We start from the all 1 vector, where we mean now by 1 that we use the top edge, and by 0 we mean we use the bottom edge. And now what we can do is we can just only switch in the first component. And then, as I was saying, we can switch back to the top edge in the first pair in the first component, while we still switch to the bottom edge in the second component. Then we again switch in the first component. And then we switch in the third component, so we switch now from the 4 down to the 0, but at the same time we switch back to 1 plus 2 in the first two edges. So also this is again an improvement, but the improvement is still only by 1. So how long will the sequence be? The initial cost is, as I was saying, 2 to the k plus 1 minus 1. We have an improvement of 1 in every step. And the final cost will be 0, so the length of the sequence will be 2 to the k plus 1 minus 1, and this is about the number of, this is nothing close to the number of strategies, which was only 2 times k plus 1, so that's only linear in k, but it's rather exponential in the number of strategies, because it's exponential in k. So the point here is we cannot actually bound the length of the improvement sequences only in terms of the number of players and number of strategies, or number of resources, to be precise. So this doesn't rule out that there is an upper bound in the number of strategies, but to make it short, there is none. So this is only a toy example to show you what can happen. There are more complicated examples which actually show that, well, it is generally hopeless. In just bad, there are bad things that can happen, so that improvement sequences will actually be long, and not only one, there will not only be one long improvement sequence, but eventually all improvement sequences will be long. So still, it is an interesting question whether we can bound the length of improvement sequences if we have further assumptions. And indeed, this is possible. And this will be our first positive result. Namely, we will consider a special class of congestion games for which we will actually give an upper bound on the length of any improvement sequence, which is polynomial in the number of resources and in the number of players. So we now want to bound the number of improvement steps in a certain class of games, and this class of games that we will be considering is the class of Singleton congestion games. What is a Singleton congestion game? Let's define that. A congestion game is called Singleton if for every player and every strategy of this player in his or her strategy space, this strategy has cardinality exactly 1. So recall that strategies are exactly, or every strategy is a subset of the resources, and now we say that every strategy takes exactly 1 resource. This is nothing like the congestion games that we've seen before, because there every player had the choice of many resources, or meaning that the strategies were larger subsets of resources. But still, this is an interesting class, and let me give you a quick example of such a singleton congestion game, which tells us that also those are meaningful. So in this example of a singleton congestion game, we have maybe a server farm. It is a load balancing game. So we have 3 servers in this example, and we have also 3 players called 1, 2, and 3. And each of the players can now choose to go to one of these servers. For example, the first player might have the choice between the first and the second server. The second player might have the choice between all servers. And the third player can only choose between the second and the third server. And these servers now have delays. Namely, the first server has a delay of 20 if there's 1 player on it, 30 if there's 2 players, and 50 if there's 3 players. The second server has a delay of 30, 70, and 90, whereas the third server has a delay of 15, 16, and 70. And now this might look as follows. So the first player might go to the first server, the second player and the third player might both go to the third server. What's the cost that these players incur? So both players 2 and 3, they both have a cost, each of them has a cost of 16, and player 1 has a cost of 20. And indeed, this is a pure Nash equilibrium, because no player actually can improve by unilaterally switching to a different server. Of course, the first player might actually want to switch to the third server, but that's not possible for him. The second and third player, they are actually able to switch to the second server, but this will only increase their cost. So, as you may realize, this is also at least a non-trivial example. So what can we now show for these singleton congestion games? Well, we can show that all improvement sequences have a length that is bounded in the number of players and number of resources. And it is not only bounded in that, but it is polynomially bounded. Let's write that down. In a singleton congestion game, with n players and m resources, improvement sequences. Have length O of n squared times m. How do we prove this? Well, what we do is actually a pretty smart thing, namely we move to a different game in which it is actually easy to bound the length of the improvement sequences. We do so by modifying the delays. And then what we could actually do is apply the bound that we talked about earlier, that we have the bound of m times n times the maximum delay value, the maximum absolute value of any delay function. But how do we define that? Well, what we do is we define first the set of all delay values that any delay function ever has. Let's write this as V. This is dr of k for r being an r and k being between 1 and n. So what do I mean by this? Let's see this in our earlier example. What are the delay values up here? Well, the set V would be here the ordered, we will later order this, but let's first see what delay values we have. We have a value of 20, 30, 50, 30, 70, 90, 15, 16, and 17. So this would be 15, 16, 17, 20, 30 we have twice actually, 50, 70, and 90. So these are all the delay values that we see here. So having now defined this set of all delay values, we can observe that the size of this set is at most the number of players times the number of resources. Why is this? Because there are at most m different delay functions. So for every resource we have a delay function, and a delay function has exactly n possible values. So at most there can be n times m, so number of players times the number of resource possible different values. Now we do what I said earlier, we define new delay functions. And we write dr bar of k. What is dr bar of k? That's the new delay value. And we now take dr bar of k as the position of dr of k in this sorted list of V, and by this I mean increasingly sorted. Let's go quickly back to our example that we had earlier. Here we see again the V set, the set of all values that we see, and now we do a very simple replacement. How do we do that? Well, whenever we have a 15, that's the smallest value, we now write 1 instead. Whenever we have a 16, that's the second smallest value, we write 2. 17 is the third smallest value. 20 is the fourth smallest value. 30, we actually have twice, that's the fifth smallest value, so we replace it by 5. 70 is the sixth smallest value. 50 is the seventh smallest value, and 90 is the eighth smallest value. Good. And what you now see is that these new delays are upper bounded by the size of V, which we already talked about is n times m. What we now claim is that every improvement sequence with respect to the original delays is also an improvement with respect to the new delays. How do we prove that? Well, let's consider any improvement step S, S prime. And we let player I change the strategy. We can now write SI, the strategy that player I was using before, as just the set that only contains one resource R, and SI prime as also a set that contains only one resource, R prime, because, well, we have this Singleton property that every strategy contains exactly one resource. So now this makes it much easier to rewrite the cost of this player before and after the change. The cost before, this is exactly the delay of resource R when there were nr of s players using this resource. Well, usually we would have this sum here, but we don't need this sum because there's only one term in this sum anyway. Okay. Analogously, we have the cost afterwards. That's the delay of R prime when nr prime players are using this. And what else do we know? We know that Ci of S is bigger than Ci of S prime because this was an improvement step for player I. What else do we know? We know that dr of nr of s therefore has to be bigger than dr prime of nr prime of s prime. Because, well, this is how things define. This is just a simple consequence of what's written above. But this means that dr of nr of s has to be after dr prime of nr prime of s prime in this ordered sequence. So we also have exactly the same relation with respect to these new delays d bar. And what does that mean? Well, if we now define new cost functions using the new delays, then we see, okay, this is actually also an improvement step of this player with respect to the new delays. So, this proves this claim that every improvement sequence with respect to the original delays is also an improvement sequence with respect to the new delays. Now, all we have to do is upper bound the length of improvement sequences with respect to the new delays. How do we do that? Well, one thing we could now do is just take the bound that we had before. This would already give us something. We can be a little smarter here. And how can we do that? Well, we can just upper bound the Rosenthal potential and also lower bound it. We can see that, well, on the one hand, the Rosenthal potential with respect to the new delays is, of course, always non-negative. And also, we see that we can derive an upper bound How can we do this? Well, we know that any of these delay values is at most the size of v, which is at most m times n. So we have this upper bound of number of taking the sum over all resources, then taking this sum, and then always having m times n. So this doesn't even depend on k. So we may write it like this. And how big is this? Well, every player is always using exactly one resource. So if we take the sum of the number of players using any resource, and we take this sum over all possible resources, then this will be exactly n. So this is why we're getting m times n squared. And this is exactly what we claimed. So one might now ask whether this proof actually generalizes towards something beyond singleton congestion games, and yes, it does. It generalizes to a class called matroid congestion games, in which the underlying structure of the strategy spaces have to be bases of a matroid. The proof actually works exactly as I presented this, but I guess some of you know what a matroid is, but many of you also don't know. And to then see why this works, I would actually spend most of the time defining what a matroid is and, well, trying to make you understand what this is. But if you're interested in this, you find a reference in the lecture notes to a very cool paper which not only shows how to generalize this proof, but also gives a lower bound showing that, well, if you don't have a matroid structure, then this does not work anymore, meaning that there will be long improvement sequences. So we've now discussed whether improvement sequences are short or long, but this is definitely only one way of computing a pure Nash equilibrium, which was, well, the kind of naive algorithm to start from anywhere and just follow the improvement sequences. Indeed, this is not the only way you can do this, and we will see a different algorithm to compute an equilibrium in a congestion game, well, in a different class of congestion games now. And to this end, we will use the fact that pure Nash equilibria can be considered local minima. What do I mean by that? Well, we can understand every pure Nash equilibrium in a congestion game as a local minimum of the Rosenthal potential. Let's formalize that. In a congestion game, a state S is a pure Nash equilibrium if and only if there is no state S prime such that Si equals to Si prime for all but one I, and the Rosenthal potential of S prime is smaller than that of S. So let's first talk about what this lemma means. I claim this is something we can understand as a local minimum. A state S is a pure Nash equilibrium if and only if it is a local minimum of the Rosenthal potential. And what does local minimum mean? There is no better state S prime within some neighborhood of S. And we define the neighborhood now as the set of all states S prime, which are the same except for what one player does. So this is what we wrote down here. State S is a pure Nash equilibrium if and only if there is no state S prime such that, well, all players except for one player do exactly the same and the Rosenthal potential decreases. You see that a global minimum of the Rosenthal potential definitely fulfills this. A state that minimizes the Rosenthal potential, for this there cannot be a different state which has a smaller Rosenthal potential, and therefore this is immediately fulfilled. But there are also other states which might be local minima but not global minima. So let's prove this lemma. How do we prove this? Well, we show that S is not a pure Nash equilibrium, if and only if there is a state such that Si is equal to Si prime for all but one I, and the potential is smaller. So let's prove this. We'll have to show two directions. We'll start with the direction that if this condition is fulfilled, then we don't have a pure Nash equilibrium, and that's rather straightforward. Actually, both directions are rather straightforward if you know what we're doing, if you understood what we did last time. Let's recall what we know about the Rosenthal potential. We know that if the states S and S prime differ in only one component, and then this exactly corresponds to the cost difference of this of the one player changing the strategy. This is what we proved in the first lecture. So Rosenthal's theorem implies that phi of S prime minus phi of S is equal to Ci of S prime minus Ci of S. Because all players except for player I do exactly the same. Now, what do we know about this left-hand side? Well, this left-hand side, this has to be negative. And this means that Ci of S prime is definitely smaller than Ci of S. This means that Si cannot be the best response against S minus I. Okay. And this means that S is not a pure Nash equilibrium. The other direction, if S is not a pure Nash equilibrium, there has to be a player who's not playing a best response. This means there have to be a player and a strategy such that the cost of this player when unilaterally changing to this new strategy is strictly smaller than before. What does this mean? Well, let's call this state here S prime. Then we know that Ci of S prime is smaller than Ci of S, and this also means that the Rosenthal potential of S prime is smaller than the Rosenthal potential of S, just because the difference is exactly the same. The difference of the Rosenthal potential exactly matches the difference of the cost. And this is exactly what we claim, that there is this state S prime for which all players except for one do exactly the same, and this state S prime has a smaller Rosenthal potential. This is possible if there is no if the state S we were starting from is not a pure Nash equilibrium. So we've now shown this lemma. Once again, a state S is a pure Nash equilibrium if and only if it is a local minimum of the Rosenthal potential. So one way to compute a pure Nash equilibrium is now pretty straightforward, namely just minimize the Rosenthal potential. Find a state that minimizes the Rosenthal potential function. This is not always easy, but we will now see one case in which this is actually possible. And these are so-called symmetric network congestion games. So what is a symmetric network congestion game? We assume that there is a directed graph a source and a sink node, and sigma I, the set of resources is equal to the set of directed edges, and sigma I, this is exactly all ST paths. And of course we have, as usual, we have delay functions now for every edge, because we once again have edges in our graph as our resources. And we also assume that this is a monotone function. This is different from our assumptions before, because so far we just didn't care whether this function was monotone or not, but now we want it to be monotone, and to be precise, we want it to be non-decreasing. So we've seen symmetric congestion games before, namely we've seen this initial example in which we only had one player wanting to get from S to T, and also there we saw that there were long improvement sequences, that there were many states, yet still, as we will show now, in such games it is still easy, or kind of easy, to compute a pure Nash equilibrium. And how can we do this? Well, all we do is we minimize the Rosenthal potential. and we find a global minimum to the Rosenthal potential. So we show that in symmetric network congestion games with non-decreasing delay functions there is a polynomial time algorithm that minimizes the Rosenthal potential of the state. How do we do that? So once again, I hope we are it is clear that minimizing the Rosenthal potential, globally minimizing the Rosenthal potential, is sufficient to finding a pure Nash equilibrium. Not every pure Nash equilibrium corresponds to the global minimum or a global minimum of the Rosenthal potential, but definitely the other way around. Any global minimum corresponds to the to a pure Nash equilibrium. How do we do that? Well, what we do is we now replace the graph of the network congestion game in a way that we then find a min-cost flow, that we then want to find a min-cost flow, and with this min-cost flow then we immediately minimize the Rosenthal potential. And the set E prime, the new edges, those are now n parallel copies of each directed edge we have in our original graph. Each edge has a capacity of 1. So by that I mean each new edge. And sending 1 unit of flow along the ith copy of an original edge costs the delay of this edge when there are I players using this. So what does this now look like? Well, let's see this in an example. We have some nice graph we start from in our symmetric network congestion game, and there's a delay function on each of the edges. And we now translate this into the following graph. This was a game of 3 players that we had here. So we now have 3 copies of every edge. And now we just write down all the numbers that we had here. So what we now do in this graph is pretty easy. If you know the correct algorithm to do this, we now find a min-cost flow to route n units of flow from S to T. Cool. This can be done in polynomial time. I won't be talking about algorithms for this. This is what you will learn about in other classes where you learn about flow algorithms. You will learn how to do this in polynomial time. Let's, for today, just assume that we can do this in polynomial time. And then what is also known is that this will be an integral flow. This means in this graph, because every edge capacity is exactly 1, every edge is either used or is not used. And what will this minimum flow now do? In this graph, it will definitely prefer the cheaper edges over the more expensive edges among the parallel edges. So it might, for example, take here this 1 and 2 edge. Here it may take the 4 edge. And then maybe 1 unit of flow goes right here, so we have also 1 unit of flow along this 1 edge, and then 1 unit of flow along the 1 edge, 1 unit of flow along the 2 edge, and 1 more unit of flow along the 7 edge. What we can now do is we can decompose this flow into n paths from S to T. And these are exactly the strategies that our players will be using. The interesting thing is now that the cost of the flow is equal to the Rosenthal potential that we're getting. Why is this? Because, well, the path definitely prefers the cheaper edges over the more expensive ones. And this means that we first, if there's a unit of, let me go back to the example, maybe it's easier to explain. If there is like 2 players going from S to this intermediate vertex, then we have one unit of flow going by this 4 edge and another unit of flow going by this 5 edge. And this means the cost that contributes to the cost of the flow is exactly 4 plus 5, but this is also exactly what this what the original edge contributes to the Rosenthal potential in our congestion game if 2 players are using this edge. By the way, here it is important that the delay functions are non-decreasing. And because now the cost of the flow is equal to the Rosenthal potential, minimizing the cost of the flow corresponds to a global minimum of the Rosenthal potential. So this concludes our class for today. We've seen 2 different ways of actually computing pure Nash equilibria in polynomial time for special classes of congestion games. The first one were Singleton congestion games, for which we could just follow improvement sequences because all improvement sequences are polynomially bounded in their length. And then we saw another algorithm for computing pure Nash equilibria in symmetric network congestion games. In these, improvement sequences may be actually long, at least there might be some improvement sequences that are long, but still there is an algorithm that just computes a global minimum of the Rosenthal potential, and because computing a global minimum of a Rosenthal potential means in particular also computing a local minimum of the Rosenthal potential, we definitely also computed a pure Nash equilibrium this way. As I was saying, in general, computing pure Nash equilibria is difficult, and this is something that we will cover later in this class, because then we first have to define what does it even mean to be difficult here. We'll have to define new complexity classes which are probably unknown to you because it's not the usual notion of NP, because this wouldn't make any sense here. NP is always about a yes or no question. There is no reasonable yes or no question when it comes to computing an equilibrium because there is always one. But this is something that we will cover later in this class. I hope you learned a lot today. Thank you very much for your time.